This circuit simulates the forward and reverse biasing of a diode. A diode will either allow or prevent current through the lamp, depending on the polarity of the applied voltage across it. When the polarity of the battery is such that electrons are allowed to flow through the diode is said to be forward biased. When the polarity of the battery is such that electrons are not allowed to flow through the diode is said to be reverse biased. A diode may be thought of like a switch, closed when forward biased and open when reverse biased. The arrow shown in the diode symbol points in the permitted direction of conventional current flow, positive to negative. This holds true for all semiconductor symbols possessing arrowheads. The simulation is turned on to observe the biasing characteristics of a diode. When the diode connected forward biased, the current flows and the light turns on. When the connections to the diode are reversed, no current flows and the light is off. This circuit simulates the principle of operation of a bipolar junction transistor, a BJT. The circuit has been designed to demonstrate how a BJT acts as a current amplifier. It consists of three sections of semiconductors: an emitter, a base, and a collector. The base region is very thin, so a small current in this region can be used to control a larger current flowing between the emitter and collector regions. A small current flowing from the base to the emitter results in a larger flow from the collector to the emitter. Two types of BJT transistors are NPN and PNP. An NPN type is used for this simulation. NPN and PNP transistors operate in a similar manner, their biggest difference being the polarity of the voltage applied to each of them. The simulation is turned on to observe the basic operating characteristics of the BJT. This circuit simulates the principle of operation of an insulated-gate bipolar transistor, an IGBT. The circuit has been designed to compare its connection and operation to that of a BJT and MOSFET. An insulated-gate bipolar transistor, IGBT, is a cross between a bipolar transistor and MOSFET. The IGBT has the output switching and conduction characteristics of a bipolar transistor, but its voltage is controlled like a MOSFET. In general, this means it has the advantage of a high current handling capability of a bipolar with the ease of control of a MOSFET. The type being used for the simulation is a depletion type insulated-gate bipolar transistor. The simulation is turned on to observe how it operates. This circuit simulates the operation of a silicon-controlled rectifier, or SCR. The circuit has been constructed similar to the SCR circuit shown. The anode of the SCR is connected so that it is positive with respect to the cathode, or forward biased. Momentarily closing the on switch applies a positive voltage to the gate of the SCR, which switches the anode to cathode circuit into conduction, thus turning the lamp on. Once the SCR is on, it stays on even after the gate voltage is removed. The only way to turn the SCR off is to reduce the anode-cathode current to zero by opening the off switch to remove the source voltage from the anode-cathode circuit. The simulation is turned on to observe the control operation of the SCR. This circuit simulates the operation of a triac switching circuit. Maximum output is obtained by utilizing both halfways of that AC input voltage. The circuit provides random, anywhere in the half cycle, fast turn-on of AC loads. When the switch is closed, a small control current will trigger the triac to conduct. The gate resistor is used to limit gate current to a small control current value. When the switch is then opened, the triac turns off. When the AC supply voltage and holding current drop to zero or reverses polarity. In this way, large currents can be controlled even with a small current rated switch, because the switch will have to handle only the small control current needed to turn on the triac. The simulation is turned on to observe the control operation of a triac. This circuit simulates the operation of an operational amplifier called an op-amp. Resistor values Rin and R feedback set the voltage gain of the amplifier. Resistor Rin is called the input resistor. Resistor RFB is called the feedback resistor. The ratio of the resistance value of feedback resistor to that of the input resistance determines the voltage gain. Op-amp voltage gain is equal to R sub feedback divided by R sub N. According to the calculated gain of 10, applying an AC signal of 0.2 volt peak to peak will produce an inverted amplified signal of 2 volts peak to peak at the output. The simulation is turned on to observe the application of the input signal. Note the red scope trace represents the input signal, the blue trace the output. The amplitude of the output signal is 10 times that of the input. This circuit simulates the operation of a half-wave rectifier circuit. Rectification is a process of changing AC to DC. Because diodes allow current to flow in only one direction, they can be used as rectifiers. The AC input is applied to the primary of the transformer. The secondary voltage supplies the rectifier and load. During the positive half cycle of the AC input wave, the anode side of the diode is positive. The diode is then forward biased, allowing it to conduct current to the load. During the negative half cycle of the AC input wave, the anode side of the diode is negative. The diode is now reverse biased. As a result, no current can flow through it. Thus, applying an AC voltage to the circuit produces a pulsating DC voltage across the load. The simulation is turned on to observe the rectification of the input signal. Note, the red scope trace represents the input signal, the blue trace the output. The half-wave rectifier makes use of only half of the AC input wave. This circuit simulates the operation of a full-wave rectifier circuit. During the positive half cycle, the anodes of D1 and D2 are positive, forward biased, whereas the anodes of D3 and D4 are negative, or reverse biased. Electron flow is from the negative side of the line through D1 to the load, then through D2 and back to the other side of the line. During the next half cycle, the polarity of the AC line voltage reverses. As a result, diodes D3 and D4 become forward biased. Electron flow is now from the negative side of the line through D3 to the load, then through D4 and back to the other side of the line. The simulation is turned on to observe the rectification of the input signal. Note the red scope trace represents the input signal, the blue trace the output. The full-wave rectifier makes use of both halves of the AC input wave. This circuit simulates the operation of a transistor switching circuit. When a transistor is used as a switch, it has only two operating states, on and off. A low-power transistor is used to switch the current for the relays coil. When the proximity sensor switch open, no base or collector current flows, so the transistor is switched off. The relay coil will be de-energized and voltage to the load will be switched off by the normally open relay contacts. When the transistor is in the off state, the collector current is 0. The voltage drop across the collector and emitter is 12 volts, and the voltage across the relay coil is almost 0 or negligible. When the proximity sensor switch is closed, it establishes a small base current that drives the collector fully on. As a result, the relay coil is energized and its normally open contacts close to switch on the load. When the transistor is in the on state, the collector current is at its maximum value and the voltage across the collector and emitter drops to near 0, while the voltage across the relay coil increases to approximately 12 volts. Inductive loads such as the coils of relays and solenoids produce a high transient voltage at turnoff. The diode is connected in reverse bias to suppress the reverse polarity counter voltage when the coil goes from the on to off state from becoming high enough to damage the transistor. The simulation is turned on to observe the switching action of the transistor. This circuit simulates the operation of a transistor amplifier circuit. An amplifier is a device that takes a signal and increases its amplitude. The input signal is injected between the base and emitter. The output voltage is taken from between the collector and emitter. As the input signal increases the base current, it causes the output collector voltage to fall. As the input signal decreases the base current, it causes the output collector voltage to rise. The simulation is turned on to observe the amplifying action of the transistor. Note, the collector output signal is greater in amplitude than the input signal. The output is inverted or 180 degrees out of phase with the input signal. This circuit simulates the operation of a MOSFET off-delay timer circuit. With the switch initially open, a voltage is applied between the drain and source, but no voltage is applied between the gate and source. Therefore, no current flows through the MOSFET and the relay coil will be de-energized. Closing the switch results in a positive voltage being applied to the gate, which triggers the MOSFET into conduction to energize the relay coil and switch the state of its contacts. At the same time, the capacitor is charged to 12 volts DC. The circuit remains in this state with the relay coil energized as long as the switch remains closed. When the switch is opened, the timing action begins. The positive gate circuit to the 12 volt source is opened. The stored positive charge of the capacitor keeps the MOSFET switched on. The capacitor begins to discharge its stored energy through R1 and R2 while still maintaining a positive voltage at the gate. The MOSFET and relay coil continue to conduct a current for as long as it takes the capacitor to discharge. The discharge rate, and thus the off-delay timing period, is adjusted by varying the resistance of R2. Increasing the resistance will slow the rate of discharge and increase the timing period. Decreasing the resistance will have the opposite effect. The simulation is turned on to observe the time delay operation of the circuit. This simulation illustrates the operation of a programmed motor start-stop PLC program. In a PLC ladder logic program, instructions are either false or true. For this simulation, all true instructions are highlighted in yellow. The normally closed stop push button is closed, making the stop instruction true. Closing the start push button makes the start instruction true and establishes logical continuity of the rung. In turn, rung logic continuity makes the motor output instruction true and starts the motor running. At the same time the true motor output instruction closes, it makes the motor auxiliary instruction true. Once the start push button is released, electrical rung continuity is maintained by the true auxiliary instruction. The simulation is turned on to observe the operation of the program. This circuit simulates a digital signal. The circuit has been constructed to simulate a binary digital signal. The term binary refers to the idea that some things can be thought of as existing in only one of two states. These states are 1 and 0. The 1 and 0 can represent on or off, open or closed, true or false, high or low, or any other two conditions. A binary signal is generated by toggling a switch between a low and high signal value. When the simulation turned on, the generated digital signal is represented by the oscilloscope trace. This circuit simulates the operation of a two-input AND gate. The output LED will be on only when both A and B are at the high level or 1 level. The basic rules that apply to an AND gate are: if all inputs are 1, the output will be a 1. If any input is 0, the output will be 0. The simulation is operated to confirm this function. This circuit simulates the operation of a two-input OR gate. The output LED will be on only when both A or B or both are at the high or 1 level. The basic rules that apply to an OR gate are: if one or more inputs are 1, the output is 1. If all inputs are 0, the output will be 0. The simulation is operated to confirm this function. This circuit simulates the operation of a NOT or inverter gate. The NOT gate can have only one input. The result of the NOT operation is always the inverse of the input, and the NOT gate is therefore called an inverter. The basic rules that apply to a NOT or inverter gate are: if the input is 1, the output is 0. If the input is 0, the output will be 1. The simulation is operated to confirm this function. This circuit simulates the operation of a NAND gate. An AND gate with an inverted output is called a NAND gate and operates as an AND gate followed by a NOT gate. The NOT function connected at the output of an AND gate will invert the normal output result. The basic rules that apply to a NAND gate are: if all inputs are 1, the output will be a 0. If any input is 0, the output will be 1. The simulation is operated to confirm this function. This circuit simulates the operation of a NOR gate. An OR gate with an inverted output is called a NOR gate and operates as an OR gate followed by a NOT gate. The NOT function connected at the output of an OR gate will invert the normal output result. The basic rules that apply to a NOR gate are: if all inputs are 0, the output will be 1. If any input is 1, the output will be 0. The simulation is operated to confirm this function. This circuit simulates the operation of an exclusive OR, or XOR gate. The output of this circuit is high only when one input or the other is high, but not both. The exclusive OR gate is commonly used for the comparison of two binary numbers. The basic rules that apply to an XOR gate are: if both inputs are different, the output will be 1. If both inputs are the same, the output will be 0. The simulation is operated to confirm this function. This logic circuit simulates the combination logic circuit for the Boolean equation of A or B ANDed with C. The simulation has been constructed similar to the combination logic circuit shown. Also shown is the relationship between the relay ladder schematic and the equivalent combination logic gate circuit. This logic control scenario requires that the output be energized whenever limit switch LS1 or LS2 is closed at the same time as the pressure switch PS is closed. The simulation is operated to confirm this function. This circuit simulates the combination logic circuit for the Boolean equation the quantity A and B ORed with C is equal to our output. The simulation has been constructed similar to the combination logic circuit shown. Also shown is the relationship between the relay ladder schematic and the equivalent combination logic gate circuit. This logic control scenario requires that the output be energized whenever limit switches LS1 and LS2 are both closed or limit switch LS3 is closed. The simulation is operated to confirm this function.